Testing, 1, 2, 3. Can you hear me? Yeah, good.
Okay, so pleasure to start. Okay, it's a pleasure to introduce Marc Favata to this numerical-related workshop. Known Marc for a long time, and it's been a pleasure. He sort of pushed the post-Newtonian program to, especially the study of what is the memory effect, about which we'll make a small presentation in the other part of the workshop. So it's a pleasure to hear Marc tell you about post-Newtonian.
Okay, thank you. Thanks to the organizers, especially Ajit, for inviting me. I've had a great time interacting with everyone here, and it's been great to finally visit India. I've wanted to come for a long time, so I checked that off my list. Today I'm going to give you an overview of basically analytic approximation methods used to address the two-body problem in general relativity. So here's the rough outline of what we're going to do. So I'm going to give a brief overview of gravitational waves, their properties, and their sources. So let me apologize in advance to most of the people in this room who are gravitational wave experts. I'm going to sort of have a bit of a review. In fact, for most of the experts, I would say most of the entire talk is going to be stuff that you've heard already and already know. Then I'll move on to talk about motivation for why we need accurate models of gravitational wave sources. And then specifically, where do analytic techniques come in, with a focus on coalescing compact binaries. And I'll talk about why we need various analytic methods as opposed to just using numeric relativity. And I'll go through some of the different methods: post-Newtonian, black hole perturbation theory, the effect of one body and phenomenological waveform approaches. And then I'll talk at the very end about areas where further work is needed. Okay? And I should just add a caveat that I won't be able to go into too much detail, so my aim is to go broad rather than to go deep. And also, I'm not necessarily the world's expert on all these areas or any of these areas, and many of the experts are actually in this room, so feel free to correct me if I make any errors. Okay, so gravitational waves in brief. Here's the main things you should know about gravitational waves. They're ripples in the curvature of space-time. They propagate at the speed of light and are predicted by Einstein's theory. They're produced by matter and energy that moves at very relativistic velocities. And we know that gravitational waves exist because we've observed binary pulsars, and by monitoring the decay rate of the orbital period of these binary pulsars, we can infer that the change in the orbital period matches exactly the prediction that Einstein's theory predicts if this decay is due to the emission of gravitational waves. But we're not content with just observing gravitational waves indirectly through these binary pulsar systems. We'd like to detect gravitational waves directly here on Earth so that we're able to observe a wide variety of systems that aren't these individual pulsars. And sort of the most exciting thing about gravitational wave astronomy is that we've seen in the history of astronomy that every time we've opened up a new wave band, whether it's radio waves, X-rays, microwaves, we've been able to observe the universe in an entirely new way and have discovered completely unexpected things. So the hope is that something similar will occur once gravitational wave detectors come online. So to detect gravitational waves, you know we've been building this network of detectors. So there's the LIGO and Virgo collaboration, and they are currently upgrading their detectors after having done a decade of science runs. And so we expect around 2017 we might see the first detections from these detectors. In Japan, they're also building another detector called the Kagra detector, which is going to be a 3-kilometer long detector, but it's going to be underground, or more appropriately inside a mountain. It's the same mountain where the Super K and other experiments is housed. I actually got to go there a few weeks ago and see the tunnel that they're digging out. So they're more than halfway through digging out the tunnel, and they think that around 2018 they might do the first searches using this new detector. And of course, yesterday we heard from Bala about LIGO India, the third detector in the LIGO, or the fourth detector, I should say, in the LIGO Virgo network. And we can expect that sometime on the order of the 2020 to 2022 timescale. Of course, in addition to the ground-based interferometers, there's other ways of detecting gravitational waves. There's using arrays using radio telescope to observe various pulsars. We call this we call these pulsar timing arrays, and by observing correlated changes in the ticking rates of these different pulsars, we can infer that a gravitational wave has passed over the Earth, say. Okay, so this is something which is going on now, has been going on for a while, but they haven't seen anything yet. But some people in these collaborations predict that they might discover gravitational waves around the same time or perhaps before LIGO does. And of course, there's the often sad story of future detectors, which are always in the future. So we hope to eventually build a space-based detector modeled along the LISA design. And after this initial and second generation ground-based detectors have accomplished their goals, we hope to have third generation detectors, which Satya talked about, specifically the Einstein telescope, which is a design study going on in Europe. So there's lots of things which are in various stages of progress, and of course we have ambitious plans for the future. Okay, so let me talk a little bit more about sort of what gravitational waves are, and it's helpful, I think, to compare and contrast them with electromagnetic waves. So we have various properties on this table here and how they differ between the two types of radiation. So electromagnetic waves are essentially a field, the electromagnetic field, which propagates on the space-time geometry, whereas gravitational waves are oscillations in the geometry of space-time itself. So the nature of the substance which is doing the oscillating is quite different. The sources of electromagnetic radiation are generally very microscopic in scale. So when I look at a star, the source of radiation coming from that star is essentially on the atomic scale in the atmosphere of the star. Whereas gravitational waves are really generated by large-scale motions of massive, dense objects, like, for example, two big black holes going around each other. So both waves propagate at the same speed, the speed of light, but the wavelength of the waves produced compared with the size of the source is very different. Just like I said, for the case of a star, the wavelength of radiation from the atmosphere of a star is very much smaller than the size of a star itself. Whereas for gravitational waves, the wavelengths produced are on the order of the size of the source. So the wavelength produced by a coalescing compact binary of two black holes is on the order of the separation between the two black holes. So electromagnetic waves are very easily absorbed or scattered or dispersed, whereas gravitational waves are essentially have no dispersion or scattering. So this is what really allows gravitational waves to probe very deep inside a very dense and massive object. And ultimately, they tell us about sort of two different states of objects. Electromagnetic waves are telling us about the thermodynamic state of diffuse matter, whereas gravitational waves are telling us about the bulk motion of concentrated quantities of matter and energy. Okay, so what are we going to learn from various sources of gravitational waves? So the key source, especially for the ground-based detectors, are pairs of merging stellar mass compact object binaries, so some combination of a neutron star and a black hole. And by observing these objects and looking at their waveforms and accurately extracting parameters from the waveforms, we'll be able to get good estimates of the masses and spins of the individual neutron stars and black holes from these systems. And we'll also determine the rates at which these objects merge, which will give us a deeper insight into basically the star formation and stellar evolution scenarios. If we can see a coincidence between, say, a neutron star merger and an electromagnetic gamma ray burst, that'll give us information about what the central engine in the gamma ray burst phenomena actually is, which is not currently completely understood. By probing the waveform produced by, say, binary neutron stars, we'll be able to infer properties of the interiors of neutron stars which aren't accessible in Earth-based experiments. So we'll learn about the properties of ultra-dense matter. And we hope ultimately that we'll be able to test if general relativity is correct in the strong gravity regime, right? So far, we've really only tested relativity on solar system scales. So we'd like to be able to put better constraints on alternative theories of gravity. So there's another class of objects which we're interested in with gravitational wave astronomy, which I'm basically not going to talk about in this talk at all, except to just mention them briefly now. We could potentially observe supernova explosions, which will allow us to probe the details of the explosion mechanism and also infer information about what's the equation of state of nuclear matter. And we also might be able to observe individual compact objects, like an individual neutron star that has a bump on it, and the gravitational waves produced by a rapidly rotating neutron star with some sort of deformity.
What will be the supernova explosion rate for advanced LIGO?
Say again, why can't it?
What will be the event rate for supernova explosion for advanced LIGO?
So we can only see these basically within our galaxy, and the galactic rate is on the order of once every 50 to 100 years. So we'd have to be very lucky to basically see one with advanced LIGO.
Up to Virgo, right? No. Up to Virgo plus what can we see?
For supernovas, no. For other sources, yes, but for supernovas, I think just within the galaxy, basically. Maybe a little bit beyond, but not much.
Yeah. For the really extreme models, where you somehow manage to excite a lot of asymmetries in the core of the post-Newtonian star, possibly perhaps up to something like 10 megaparsecs, but most likely much, much closer. We simply don't know what happens in a supernova.
It really depends on the asymmetry and the right? And we really don't know much about that.
But I think even with the most asymmetric cases, the distance reach is not very high. So. The supernovas are kind of, if we get lucky, it'll be great, but let's not build LIGO because of them sort of source. Okay, so another class of sources is supermassive black hole binaries. So this is really only important for the space-based gravitational wave detectors and also the pulsar timing arrays. So if we could observe these types of objects, one of the things we'll learn is how massive black holes actually get their mass, whether it's through many mergers of smaller black holes or through accretion of gas. These systems will also have very, very high signal-to-noise ratios, which will allow us to test general relativity with very high precision, much higher than we'll be able to do with the ground-based detectors. By measuring the distance to the sources very accurately and also by getting a redshift to the sources, we'll be able to put some sort of constraint on the nature of dark energy. And another interesting source for the space-based detectors is something called extreme mass ratio inspirals, which I'll talk a little bit more about modeling later in the talk. And one of the interesting, so this is basically a stellar mass black hole, say around 1 to 10 solar masses, orbiting a supermassive black hole on the order of 10 to the 5, 10 to the 7 or 8 solar masses. And if we could observe these sources with a detector like LISA, one of the things we'll be able to investigate is what's the number density of compact objects inside of a galactic nucleus, which we can't easily probe using electromagnetic observations. And we'll also be able to make a very precise map of the space-time geometry around the supermassive black hole. Essentially, we'll be able to do the analog of geodesy around the Earth when we send a satellite around the Earth and very accurately map out the gravitational field of the Earth. The hope is that we'll be able to do something similar around a black hole and essentially test whether or not the space-time geometry agrees with the actual analytic solution to Einstein's equations. There are also various exotic sources that we might expect to see, but we really don't know how likely they are. Cosmic strings, gravitational waves from the Big Bang, and of course unexpected sources that we haven't considered. And there's also, and aside from sort of these purely astrophysical questions, interesting just sort of mathematical type physics questions we might want to try to answer, like what types of interesting nonlinear effects might manifest themselves and can we observe them in the waveform, and in what regimes are the various approximation methods we use, in what regime are they valid. I think just the observation of gravitational waves will, in addition to comparisons with full numerical simulations, also shed some light on that question. Okay, so the basic picture of a gravitational wave from a coalescing compact binary is what's shown here. As a function, if you just plot one of the gravitational wave polarizations as a function of time, you have this characteristic waveform in which the amplitude is increasing as a function of time up until the point of merger, and then it exponentially decays in this quasi-normal ringing phase. And at the same time, the frequency of the waves is also increasing with time. Okay, so we split up these phases into the in-spiral phase, the merger phase when the two black holes finally coalesce, and the ring-down phase when I just have a single black hole that's radiating away its radiation. Okay. And when we talked about this comparison between electromagnetic and gravitational waves, you might have noticed that the way gravitational waves behave, it's very much more analogous to sound waves than they are to electromagnetic waves, right? The wavelengths are on the order of the size of the object, which is true for sound waves, and they're due to bulk motions of massive objects, not microscopic scale phenomena. So one of the things interesting to do is to just make sounds of what these gravitational waves sound like. So here's some examples put together by Scott Hughes' research group. And the gravitational waves basically have this characteristic sound that we call a chirp. Not sure if you'll really hear it. You'll hear it at the end, right? So it just goes whoop, right? So you can hear this feature of the amplitude increasing with time and the frequency increasing with time. And that one I played, you couldn't quite hear it because of the volume, but when you have spin and other types of effects, that's also going to affect the waveform. So in that particular wave, if you listen closely, instead of just hearing a whoop, you actually heard a whoop, because when you have spin, when you have your two black holes spinning, for example, that introduces some additional modulation to the waveform, which you can pick out. Another one that's a little bit easier to hear is if you have eccentricity, for example. That also introduces additional features to the waveform, which you can, I think you can hear this knocking sound, this bump, 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 bump. And that's also going to increase with frequency and amplitude. And essentially what that is, when you have a very eccentric orbit, when the little black hole, say, gets very close to the big black hole, which is the type of system that's being modeled here, you get a burst of radiation. You get a much stronger burst of radiation when you come at periastron than when you're further away from the black hole. So that's why you hear this knocking, right? And over time, the eccentricity gets smaller and smaller, and it sounds more like the regular chirp sound. Okay, so by making sounds, you sort of gain a little bit more intuition into what gravitational waves are. Okay, so what's the challenge in gravitational wave astronomy? So on the experimental side, the challenge is that, for these sources I described, the typical distance by which a source is going to move the LIGO mirrors is basically a nanometer. Okay, so it's a really, really tiny displacement that we're trying to measure. And on top of that, there's all these various sources of noise in the detector which obscure our signal. So experimentally, it's a very difficult challenge. So I'm going to focus on the theoretical side, and there the theoretical challenge really comes from the fact that Einstein's equations are fundamentally difficult to solve. So ultimately what we need to do is we need to make a very accurate waveform to be able to pick out this signal from this very noisy data stream. So in order to do this, you need to compute this waveform very accurately, which basically involves solving for the motion of, say, two black holes or two neutron stars going around each other. Sounds like a chirp outside, actually. However, relativity is very much more complicated than Newtonian gravity. So let's just investigate a little bit how these two theories of gravity are different. So in Newtonian gravity, you just have Poisson's equation on the left, and in Einstein gravity, you have the Einstein field equations on the right. And so these things differ in complexity in various ways. So in Newtonian gravity, you just have a single equation in terms of a single scalar variable, and you have a very simple differential operator acting on the left-hand side of the equation. Whereas in Einstein's gravity, you have this much more complicated tensor, which is 6 independent equations, 6 independent variables, being the metric instead of just this Newtonian potential. And this operator is very, very much more complicated, has many, many, many more terms. Okay? In addition, on the right-hand side, in Newtonian gravity, it's only mass density which contributes to gravity. Whereas on the right-hand side, you have this contribution from this stress-energy tensor, in which not only mass density contributes, but also velocities contributes, thermal energy, pressure, internal stresses, electromagnetic fields, and gravity itself also contributes. So there's very many more sources of gravity in Einstein's theory. And as I mentioned before, the actual differential operator that governs the behavior of the equation is just a simple linear operator for Newtonian gravity, but this very complicated nonlinear one for general relativity. In addition to the field equation being more complex, the equation of motion that, say, governs, once I know what the field is everywhere, how do I compute the motion, right? That's also very different. So in Newtonian gravity, it's very simple. You solve this equation, get the potential, and then take the gradient of that potential, and that tells you the acceleration of your mass everywhere where you know the potential. So in relativity, you have something similar, but your equation is more complex. You have now several more equations, and they depend on this metric tensor, so it's a little bit more complicated. Okay, so how do we now solve this problem? How do we solve Einstein's equation? So there's basically 3 ways that we know of to solve Einstein's equation. One is to find an exact solution. Okay? So the problem is you can't find an exact solution for very many interesting cases. We only know exact solutions in very highly symmetric cases, and there's many exact solutions, but there's really only two useful exact solutions. There's the Kerr black hole and there's the Friedmann-Robertson-Walker spacetime. Those are really the only two astrophysically useful exact solutions, at least that I can think of. Please correct me if you know of any others. Yeah, like I said, astrophysically useful solutions. So another approach you can do is to use perturbation theory. Okay, so in particular, you can expand about some exact solution. Right. So there's two ways that we have of doing perturbation theory. There's post-Newtonian theory, in which you're expanding about flat space essentially, and there's black hole perturbation theory, in which you're expanding about the Kerr or the Schwarzschild solution. Right. In cosmology, you also can expand about the Friedmann-Robertson-Walker spacetime if you're interested in cosmological applications. And then there's numerical relativity, okay, which is essentially sort of the exact way of doing it, in which you solve equations numerically on a computer without imposing any sort of symmetries or approximation. But here you're sort of limited by essentially the fact that you have to impose some finite resolution when you do your computation. Your initial conditions are not necessarily the exact astrophysical initial condition that nature itself imposes, and ultimately you're limited by time and computing power. You can't just simulate anything that you want, at least not yet. So what's the story for numerical relativity? So this has been a problem that's been going on for 30 years or so, but it wasn't until 2005 and 2006 that a few groups around the same time were finally able to merge two binary black holes. The binary neutron star problem was solved a little bit before then, in around 2000. So the current status is basically, almost every numerical relativity group can now do binary black hole mergers, and also many of them can do neutron star black hole mergers. So I would say numerical relativity is now has become a very mature field. And in terms of what's going to happen in the immediate future, I think that in the black hole case, I think right now people are mostly focused on doing a more detailed exploration of the parameter space. Okay, so there's this NR-AR collaboration, for example, which is trying to simulate many different kinds of configurations, and the SXX collaboration that Harold's a part of has also recently simulated a very large number of possible configurations. And on the neutron star black hole or neutron star side of things, I think sort of the upcoming things are now to put in better ingredients into those simulations. Put in magnetic fields, put in more realistic equations of state, put in neutrinos. Just make everything more realistic, basically. Okay, so numerical relativity, that's really great, but why do we need these analytic methods at all? Numerical relativity can do all these wonderful things. Ultimately, as I said before, time is the thing that limits you. It's very hard to do more than, say, around 10 orbits. It starts to become very computationally costly. People have certainly done more than 10, but it's very expensive. Now, if we look, though, at how many orbits do we actually need to simulate based on how many cycles does a typical source go through while we're observing it with LIGO, if we take, for example, a neutron star binary, that's going to undergo around 8,000 cycles while it's in the LIGO band. And a black hole binary might undergo 300 cycles. So that's many more cycles than we're able to simulate with numerical relativity. Furthermore, if you look at how the orbital times and radiation reaction timescales scale, you can get a better sense as to why it's hard to do certain types of simulations. So if I look at the orbital time of a binary, just the time it takes to do one orbit, that scales like the radial separation between the two bodies to some power. And the radiation reaction time scale, the time it takes for the orbital radius to change appreciably, okay, due to gravitational wave emission, that scales like a much higher power of the orbital separation, and also scales like 1 over essentially the mass ratio. Okay? So what this means is, if I want to simulate a larger orbit, right, which is at the beginning of say when the binary enters the LIGO band, it takes very much longer to do even one orbit because the orbit is bigger, right, because of this equation here. And also it takes very much longer for that orbit to shrink because bigger orbits shrink more slowly when they're further away, and then the shrinking increases as you get closer in. Okay, so it takes longer to do an orbit and longer to do the entire in-spiral. And also, if I want to simulate objects, which is say a small black hole going into a big black hole, that's even much harder because of this 1 over the mass ratio dependence in the radiation reaction time. right? If I want to say do a solar mass into a million solar mass, right, this time scale becomes very, very long. So it's essentially very difficult to simulate things that have a mass ratio that's less than 1 to 10. And if you want to do something like these MREs, which are 1 in a million, it's basically impossible to do that with numerical relativity. So I also want to do a little bit of an aside here on why we need to have very accurate waveforms. Okay, why do we need this phase accuracy? So when we do matched filtering with gravitational waves, ultimately what we're doing is there's some true signal which nature provides, and we have some template, some inexact signal, which is our best estimate that we're trying to match with this true signal, say. Okay? So ultimately what we're doing when we're trying to detect gravitational waves is we're computing this particular inner product and trying to make this, hopefully we're making this inner product be as big as possible. Okay? You can think of this as just taking two vectors, which is your true signal and your approximate signal, right? And hopefully if you choose your approximate signal well, these two vectors are aligned parallel, but if you choose really poorly, they're perpendicular and your dot product is going to be 0. Okay? So this dot product basically has this particular form, and we can sort of investigate what happens in a very sort of contrived and specific case. So what's inside this integral here is an integral over a frequency space in which I've taken the Fourier transform of these time domain gravitational wave signals. And let's suppose I just model my true signal in this very simple way, which just depends essentially on some amplitude, which is the same in both cases for the true signal and the approximate signal. And let's just say the true and approximate signal, they only differ in, say, the phase of the Fourier transform of the wave. So, you know, this one, the true signal is off by just some small phase shift that's a function of frequency from the approximate signal. So let's take this simple model for the true and approximate waveforms and plug it in. And if you just do a little bit of algebra, you can see that you end up getting an integral that depends on some amplitude, which is weighted by the noise in your detector, times the cosine of the difference between your true and approximate waveform, essentially a cosine of this unknown piece to your template. Okay? And so now let's see what happens when we actually try to compute this integral, but when we don't know the waveform exactly. So if we just let's just ignore what the detector response is and just assume it's a constant. Essentially what you see here is suppose my signal is not very accurate. Okay? So in other words, this phase that accumulates as a function of frequency is very big. This phase difference is very big. Essentially what that does is it imposes a cosine oscillation. So what I'm plotting here is the integrand. Okay? So essentially what I'm doing is this mismatch between the template and between the true signal and the template is imposing some oscillation on the overall amplitude, which is just this is just the f to the minus 7/3, which is plotted here. So when this mismatch is very big, I get very many oscillations over the time period in which my binaries in the LIGO band, and you can just tell by eye that if I try to do this integral, it's going to be very nearly 0, right? But as I make this phase offset smaller and smaller, okay, the number of cycles due to this mismatch in the two phases gets smaller and smaller, and the resulting integral, when I take the integral of this guy and then this guy, right, I'm going to get less cancellation. Okay? So ultimately, this is the reason why we want to get this phase function to be very accurate, okay? Because this match filtering process is very much dependent on modeling this phase very well. Okay, so now I'm going to briefly go into just the various modeling techniques and sort of what are the current status of things. So the first approach is post-Newtonian theory. So the basic idea is you take Einstein's equations and just writing everything very schematically. So the equations are not precisely correct. So it's just to give you the idea. You're basically you're making some perturbation about the flat space-time metric. And you sort of start out by recasting Einstein's equations in a form which is just the regular flat space wave operator acting on this perturbed metric. Okay, and on the right-hand side, you have your stress energy tensor, and all your nonlinear terms you're essentially grouping onto this other piece. Okay, so this equation here is essentially exact. Okay, it's equivalent to Einstein's equations. I haven't done any approximation yet. Okay, but then what you do is you then expand this perturbation in some small quantity, which you can basically take to be the speed of light or the mass divided by the separation. Okay. So the actual procedure is a little bit more subtle than I'm describing here, but just bear with me. So you expand out your metric in terms of this small parameter, and you likewise expand out your stress energy tensor also in terms of this small parameter, say the velocity. And then you essentially do some iterative procedure where you take the first order result for your stress energy tensor and your first order result for your metric perturbation, and you solve it order by order, right? So you do the standard thing that you do when you do perturbation theory. Okay? And then once you know the result at first order, you can plug it back in and get the second order result, et cetera, et cetera. Okay? So it's a little more complicated than I described. I mean, in reality, you sort of need to solve this equation in two regimes. You need to solve it in the wave zone far away from the source and get some sort of multipole expansion for your wave, and then you need to relate that multipole expansion to the metric locally to your compact objects, right? So you sort of need to solve Einstein's equations perturbatively in these two regimes, and then you need to do some matching that lets you relate how does the multipole expansion far away from the source relate to some description of multipoles that are related to integrals of the stress energy tensor around my actual source. Okay, so that's sort of where all the dirty magic comes into play. Okay, so what are some of the results of this post-Newtonian program? So the first sort of useful thing you want to compute is what is the actual equation of motion of my two masses? What is the generalization of Newton's law of gravity? So that result basically looks like this. If I just have my two masses and they have some separation vector, and I express everything in terms of the total mass in this quantity eta called the reduced mass ratio, my equation of motion basically has this form where I just have the Newtonian result, and then I have these two correction terms, one of which has some velocity dependence, okay, some overall velocity dependence out front. And then what this thing looks like is just some gigantic mess. You basically have some big expansion, okay, where you can explicitly see the various post-Newtonian orders that enter, right? So for example, this 1 over c squared, that's the first post-Newtonian result. The 1 over c to the fourth is the second post-Newtonian result. The 1 over c to the fifth is the 2.5 pn result, where you first start to get radiation reaction effects, you know, and et cetera, and the expressions get bigger and uglier as you go to higher and higher orders. And they depend explicitly not only on the separation between the bodies, but also on the velocities of the bodies and on the rate of change, yeah, basically the r dot and phi dot of the two bodies. So the other sort of important result you want to compute, which you need this equation of motion for, is to compute the actual waveform, which is what LIGO is measuring. So that has also been done over the years. I apologize for not giving the references to everybody. It's just too impossible to list everything when you're surveying the entire scope of analytic relativity. But the basic structure of the waveform looks something like this, where you have some amplitude which depends on the total mass divided by the distance to the source. And there's this factor of v squared, so this is essentially where you see the amplitude of the wave increasing when you have your chirp, right, because the velocity is getting higher and higher. And then you have some dependence on your orientation of the binary, okay, with respect to the detector. And then you have the main piece, which is the phase evolution of your signal, okay? And the phase evolution is really the critical thing that we want to compute. And that also looks like some slightly less ugly mess. And this has been basically computed now to 3.5 post-Newtonian order. Okay, so when I say some post-Newtonian order, when I say one post-Newtonian order, that means a power of v over c squared beyond the leading order result. Okay, so this phase function, right, it has some initial contribution, which is really due to this 2.5 pn term in the equation of motion, which causes radiation reaction. Okay, this is what makes the phase, you know, differ from just a circular Keplerian orbit, okay, and actually make it in spiral. And then you have various post-Newtonian corrections, which come in at all these various powers of v over c, up to this v to the seventh, which is the 3.5 pn term. And the frequency of your waves is essentially encapsulated in this v. You can essentially replace v with some power of the frequency. And so to illustrate why it's important that we actually compute this post-Newtonian series to all these terms, it's useful to look at what is the number of cycles contributed by, say, a specific kind of binary that LIGO might expect to see. What does the contribution do to each of these individual terms, right? So most of the effect you see comes from just this Newtonian term here. For, say, a 10 solar mass binary black hole merger, in the LIGO band, you get 600 cycles just due to this term, but you still get a decent number of cycles, around 60 cycles, due to the second term, and likewise you can see how many cycles you get for each term. And even the highest term that we've computed so far, this 3.5 pn, still contributes on the order of 1 cycle. Okay? And even a phase difference on the order of 1 cycle is large enough to essentially screw up your template to some degree. If you want to make a very accurate estimate of the parameters of your signal, I think you actually need to know a little bit better than 1 cycle. Okay, so that's sort of the simple case of circular waveforms. So now let me just talk about what happens when you go beyond simple circular waveforms. The first effect you get is even when you have circular waveforms, it's not as simple as I just described. In addition to having this gravitational wave signal that occurs at twice the orbital frequency, okay, you also have higher harmonics of that signal that happen at other multiples of the orbital frequency, from 0 times the orbital frequency, 1 times the orbital frequency, 2, 3, 4, 5, etc. Okay? But typically these amplitude, we call these higher harmonics or amplitude corrections, these are typically suppressed by a factor of V over C for these higher harmonics. Okay, so what we call the 2-2 mode, or this mode that occurs at twice the orbital frequency, is really the dominant effect. But these other higher harmonics can also be important for improving your ability to pick out these signals. So it's useful to model them, and Arun and other people have, in this room, have spent a lot of time working on that. There's an exception to the statement I said that these factors, these higher harmonics, are suppressed, and this is this other weird type of mode called the memory mode, or the nonlinear Christodoulou memory effect. This is essentially a zero frequency contribution to the gravitational wave signal, which slowly increases with time. But this effect, even though it comes from this complicated nonlinear interaction, it actually affects the waveform at leading order in the amplitude. So it's not a higher order effect in the post-Newtonian scheme like these other higher harmonics. So I'll talk more about this another day. So I'll talk about this in the next talk that somebody has asked me to give. Okay, so that's again circular non-spinning orbits. So what happens when you have spin effects? So now when you have spin, okay, if you still restrict the circular orbits, the equations of motion still become somewhat simple. They're more complicated than when you just have purely circular orbits, but the equations of motion still take a regular, reasonably simple form. But there are various complications that I'll now discuss that comes in. So in the case when you just have, say, the two spins aligned or anti-aligned with the orbital angular momentum, things are still only slightly more complicated than in the regular circular case. For example, if you want to solve for the phase evolution, or essentially equivalently the evolution in the orbital frequency as a function of time, you just have to solve this single differential equation. It's just some function of frequency, but also depends on the spins, but these are essentially constants. Okay, so it's really just the same type, slightly more complicated differential equation. Okay. So when you have non-aligned spins, that's when it suddenly becomes much more complicated, because now you can have precessions of the spin vectors themselves. Okay, everything doesn't just stay at constant magnitude and orientation. The magnitude of the spin vectors stay constant, but they can start rotating around. Okay. And so now to model this, it's not as simple. You now have to solve two more differential equations that govern the spin evolution. And now things really have to be done more fully numerically. You can't really do it completely analytically in the fully general case. There are cases when you can make analytic approximations, but in general, now everything has to be done numerically. You're not going to get a very simple waveform anymore. And essentially the effect of having this spin is to cause variations in both the amplitude and the phase on a time scale that's related to what this precession time scale of these two spin vectors is. Okay, so your waveform, instead of looking like that simple chirp, looks like something more like this now. Okay. In addition to sort of this precession, again, there's also higher harmonic effects that come in. So corrections to the amplitude due to these spin effects, okay, and these have been computed by Arun and his collaborators, and also for the memory effect, we've computed this. So these types of corrections to the amplitude and higher harmonics when you have spin are now reasonably well understood.
Sorry, even if you have precessing spins, so you have like a DC shift in the memory then, or?
Yeah, you still have this memory effect. It's just that there's an extra, it's just a little bit different because you have spins, right? And you could have some additional modulation to the memory because of because of this spin effect. Yeah.
Does that be then easier to measure than just a pure DC? If you have
Um,
modulation memory, then it might fit.
Yeah, potentially. I mean, we haven't actually looked at the detectability aspect of it, but yeah, potentially that helps. But I think that effect is going to be smaller, even though there's this modulation. You know, I think it's still a difficult to measure effect. I don't think it.
So it's a modulation on the build-up of this DC term. But once you build up, it stays there. It's a DC term again.
That's right. That's right. It goes. That's right. Eventually, you still get this plateau, but I believe there's some oscillations on top of this secularly increasing piece.
So apart from this modulation on the envelope by the precession, we have an additional modulation to the memory.
Not that I have thought of in detail. I have to say we haven't. You know, we've spent a lot of time investigating the aligned case and very briefly investigated the processing case. So I don't want to make any firm statements about exactly how it behaves. Okay.
Sorry, not to drag you too deeply into this, but why is this called the memory effect? I mean, can you just explain?
Yeah, sure. I'll talk about this in more detail later. But the basic idea of why we call it a memory effect is you've probably seen this standard picture of when I have a gravitational wave. If I imagine having a ring of ping pong balls and I have a gravitational wave pass through, I get some ellipsoidal distortion of these ping pong balls with time, okay? And if I have a regular wave without memory, okay, when this wave has passed by and the wave is now gone, my ring goes back to a circle, okay? I no longer have this ellipsoidally distorted shape. But if I have a gravitational wave with memory, basically a wave that looks like essentially an S-shaped function, okay, what essentially happens is my ring of ping pong balls can be permanently left in this ellipsoidally distorted configuration. So we say that the detector, this idealized detector, has a memory that the gravitational wave has passed by.
So if I consider gravitational waves from hyperbolic passage,
Uh-huh.
I'll get exactly that too.
Yes, that's another kind of memory effect. Yes, that's right. Yeah, there are several, say,
This pass through.
sort of, yes. I mean, it's essentially, except the actual, you're only really sensitive to the shift in the metric, okay? Just a metric which has just been shifted, if I just have the Minkowski metric and I just shift it to another constant value, that can be absorbed into a gauge transformation, okay? So you're not able to observe essentially, a flat metric that's different from Minkowski. You can only observe this shift between the metrics and these two, from these two time periods. Okay, so that was for circular orbits. Okay, so then you might want to worry about eccentric orbits. So typically we don't really worry about this very much in gravitational wave astronomy because gravitational waves have the property that they damp away eccentricity. So if I have an eccentric binary, the eccentricity gets smaller and smaller and smaller as the binary inspirals. So for example, if I look at all the binary pulsars and look at all their eccentricities now, and I can project what eccentricity will they have when they enter the LIGO band millions of years from now, the largest one will have an eccentricity on the order of 10 to the minus 5 when it enters the LIGO band. So we expect eccentricity to generally be small, but there are various scenarios that astrophysicists have come up with in which you might get binary neutron stars, say, or binary black holes that do have non-negligible eccentricity when it enters the LIGO band, especially binaries that form through dynamical capture situations. Okay? So what happens when you have these eccentric signals? So the first effect that you get is periastron precession, right? The familiar effect that you just see with Mercury, which comes in as a 1pn effect. You also get eccentricity-induced modulations to the orbital phase and the amplitude. This is just a Newtonian effect. Essentially, the fact that the orbital phase is now, my speed of my binary is essentially changing depending on my position in the orbit. That introduces an additional modulation, and there are various post-Newtonian corrections to essentially that effect, okay, which have been worked out by various people. You also get, just like in the case of circular orbits where you have these contribution of power at higher harmonics, you also get the same effect in eccentric orbits, except in the eccentric case, it happens even at leading post-Newtonian order. So at 0pn order, right, you can still get gravitational waves at frequencies that are not twice the orbital frequency, okay? And what frequency where the peak amount of power comes from depends on what the eccentricity of your binary is. So a very highly eccentric binary is actually going to have a gravitational wave which has its strongest peak in the Fourier domain at a gravitational wave frequency that is many times the orbital frequency. Okay? So you have this additional structure to the harmonics of your signal. Okay? And in addition, you have post-Newtonian corrections on top of these various harmonics to the signal. Okay? So there are various corrections to, say, the energy flux and the angular momentum flux when you have eccentric binaries. So the expressions are very much more complicated, especially when you can consider tail effects. And it's necessary to compute those corrections in order to get what's the secular changing phase contribution to this inspiraling eccentric binary. So these have been worked out by many people in this room. Okay? But now in this case, things are numeric, okay? Because these equations are more complicated. You again don't get, if you want to get the exact, the full solution as a function of time, you really have to solve now a system of differential equations, okay? You can't just write down a simple formula anymore. Except in the small eccentricity limit, you can still do things anyway. Okay, so that's eccentricity. Okay, what's another effect we might want to put in? So there's tidal interactions. So that's another effect which has been had a lot of interest in the community recently. So the basic idea here is, suppose I just have the Earth and I have the Moon over here. The Moon, we know, tidally deforms the Earth. Okay, so now the Earth's gravitational potential isn't just, say, m over r. It's m over r plus some 1 over r cubed correction, which depends on what's the size of this, what we would say an induced quadrupole moment, a tidally induced quadrupole moment on the Earth. And the same thing happens if I have, say, a binary neutron star. One neutron star is going to tidally distort the other neutron star. Okay, and now the first neutron star is going to feel a different gravitational potential, so its orbit is going to be different, and its gravitational wave signal is now going to be different. Okay? So the way we parameterize this, this distortion is through this quantity called essentially the Love number, or the tidal distortion parameter. It's basically a way to linearly relate, if I put my neutron star in some sort of tidal field, what is the corresponding linear response of that star in terms of its induced quadrupole moment. So that relationship that defines this, this Love number quantity is written here, where this tidal field just looks like your sort of standard Newtonian tidal effect. And this Love number quantity essentially depends on the radius of your neutron star to the 5th power times some coefficient, which is really what's called the Love number in sort of the solar system dynamics literature, which depends on what's the equation of state of your neutron star. So if you can measure what this number is, you're going to get some sort of information on what's the equation of state of a neutron star. So that's why we want to sort of put this into the waveform and figure out what it is, because we'll be able to make this kind of constraint. So this has been the subject of many, many studies, which I won't go into. So in terms of where this enters actually at a very high post-Newtonian effect in the phasing. So if we look at the orbital phasing, before I showed that 3.5 pn expression, okay, now the tidal effect actually enters. So this is the expression I showed earlier, where I'm just rewriting the coefficients in terms of these c's. Okay, now the tidal effect actually enters at this power v to the 10th, okay, which is a 5 pn effect. So you can see this Newtonian tidal effect essentially comes in at a higher pn order than we actually know the rest of the waveform. So there's all these other pieces of the waveform that we don't know, okay, which come in at lower orders. So this presents a possible problem. Okay, so there are other corrections to this tidal effect as well. This is just the leading tidal effect, which comes in at this 5 pn order, but there are post-Newtonian corrections to that tidal effect, which come in at this 6 pn order. There's also an octupole tidal distortion. This is just the quadrupolar tidal distortion that I've been talking about so far, but there are other types of tidal corrections which come in at higher pn orders, which you can work out, but this is the piece that we're most sensitive to. But there's this problem that we don't know what these lower order coefficients are. So if we're trying to measure this tidal effect, we're essentially trying to measure this piece of this coefficient, but we don't know all these other pieces of this series. That introduces some sort of systematic error when we try to use post-Newtonian theory to estimate this Love number. So if I have time, I'll talk a little bit more about that later.
Arguments that these tidal terms are expected to be larger than these higher order Newtonian terms?
Are there arguments that they should be larger?
Yeah.
Well, you can make an estimate for what these terms are,
Right.
okay, just based on, say, the black hole perturbation theory limit, okay, which I'll talk about later, right? And so if you do that estimate, these terms are not negligible compared to this term. Okay, so, I mean, these tidal terms are actually much larger than you might expect them to be, because this Love number parameter, if you write it in a dimensionless way, is actually quite a big number, which is why we're able to actually even think about detecting this effect at all. But these other terms are actually much, also very big. This term is not so big that it dominates these lower order terms. Okay.
So all this work is trying to say something about equation of state from this, have this lacuna?
It depends. If you're only using post-Newtonian waveforms to do this, then yes. Okay. If you're using numerical relativity to do this, then no. If you're using only a numerical simulation, then no. If you're using EOB calibrated to a numerical simulation, then I think probably that's okay too. Okay. So there's a caveat as to where this problem arises.
Those potentials, can I decouple them as a conservative part and a reactive part, or they are all mixed up?
What do you mean? This potential, or I'm not sure what potential you mean. What higher order specific? What do you mean?
So, for example, the connections to this, all this is a phase evolution.
Yeah, this is in the phase. Yeah.
If you consider in terms of the potential,
Uh-huh.
they are higher order. Some
Uh-huh.
of the contributions will make the binary to spiral or out spiral. The other one can, the other one will be associated with certain quantity. Can we make the distinction?
I don't know. Is the short answer. You're saying there's a. I mean, ultimately, this is a dissipative effect which is entering in here, right? You're saying, is there a conservative correction to the phasing, which comes from this tidal effect?
The potential can contribute to conservative part of the orbital evolution, as well as
That's
the
right.
reactive parts.
Right. That's right. So what are you at?
No, if they can separate these two, that may be easier way of, because the phase evolution will not be that much dependent on the conservative part.
So I'm not quite sure how to answer your question. I mean, you have to compute both the conservative piece. I mean, ultimately, you have a conservative, this tidal distortion produces a conservative correction to your potential, right? That affects your orbital dynamics, right? And then that conservative correction, okay, that folds into when you're computing the multipole moments. So it sources a dissipative effect. So I guess I don't quite understand where you get the two different. Okay, we can talk about it later. Okay, so I talked about this post-Newtonian method. Okay, so the first interesting thing you might want to do once the numerical relativity works is compare these post-Newtonian waveforms, compare with the numerical waveforms, and generally they compare, fairly well up to some specific point. Okay, which you can quantify. And the further out you go, typically the better. So you can see here, these were aligned, the numerical and post-Newtonian waveforms are aligned at some specific point. So for a large part of the in-spiral, it agrees pretty well, but at some point towards the end of the in-spiral, as you expect, it breaks down and no longer becomes good. And this is for equal mass systems. If you look at spinning systems, the agreement tends to be worse. Okay, so this is some recent work which I'll refer you to in the spinning case. Okay, so that was all I wanted to say about post-Newtonian. Okay, so now in the remaining 5 or 10 minutes, I'll cover the remaining 60% of my talk. So now let's talk about black hole perturbation theory. Why do we need to use black hole perturbation theory? So we want to be able to treat this other class of objects, which are a small compact object going around a big black hole. Okay, and the problem here again is I have this small mass ratio, so this little black hole is going to be doing thousands or millions of orbits around this big black hole. Okay, and on top of that, this little black hole is in the very strong field regime, very close to the horizon of the big black hole. So I can't really apply this post-Newtonian approximation because now V over C is no longer small, and on top of that, these post-Newtonian series have the property that they converge more slowly in the small mass ratio limit. Okay, so on two ways, these post-Newtonian approximation doesn't work very well. And I can't use numerical relativity because I need to simulate hundreds or millions of orbits, and I just can't do that. Okay, so what do? I use perturbation theory, where I start with, say, Kerr-Schwarzschild, and I perturb about Kerr-Schwarzschild in terms of the small parameter, where now my small parameter is going to be Q, the mass ratio. So the little black hole divided by the big black hole, which is going to be some very small number. And when I do this, when I now iterate through Einstein's equations, I now can get a essentially separable wave equation for either the metric perturbation in Schwarzschild or for the curvature perturbation, something related to the Riemann curvature tensor in the case of rotating black holes. And this has been known for a very long time by all these famous people who worked on this. Okay, so you get some sort of linear differential operator, say, acting on your metric, and that's sourced by the stress energy tensor of my point particle. Okay, so a lot of work has then been done to simulate, basically to solve this equation and produce gravitational waves. Okay, so the first big body of work that was done has been to compute waveforms from this type of scenario in a situation in what's called the radiative approximation. Okay, and what that means basically is I take this equation here, okay, and I plug in for my stress energy tensor a geodesic orbit. So I put in, say, a Kerr geodesic. I specify some energy, angular momentum, and Carter constant. Okay, I compute an orbit. I then compute what's the wave produced by that orbit. Okay, once I know what that wave produced by that single orbit is, okay, I can then compute what's the radiation emitted. Okay, and that radiation also tells me what's the rate of change of energy, the rate of change of angular momentum, rate of change of Carter constant. Okay, so once I know the radiation field for a given orbit, I can then essentially update what's the constant of motion for that particular orbit, and how does it take me to the next orbit. Okay, so once I compute these fluxes of energy, angular momentum, Carter constant, I now shift myself to the next orbit. Okay, that's a little bit inner, say, right? And I iterate this procedure, and I generate a sequence of geodesic orbits, which I then string together, and I know what the waveform is at along each orbit, so I can string that together, and I can produce a waveform as a function of time for the entire in-spiral. Okay? So in addition to this procedure, which you have to do numerically, by numerically solving this separable PDE, which you can turn into an ODE, okay? Other people have also been able to do this procedure analytically if you make the post-Newtonian limit, okay? So you're still using this radiative approximation, but you're able to, if you assume in addition that the velocities are small, you can actually analytically solve everything, okay? Where now you're in the approximation that I'm only at leading order in the mass ratio. So I don't have any corrections to the mass ratio like I have in the post-Newtonian, in the standard post-Newtonian case, okay? But the advantage is I'm able to now take these post-Newtonian calculations up to very high post-Newtonian order. So these were done to the order of 4 PN, many decades ago, and recently have been computed up to 22 post-Newtonian order for just a point particle going around a Schwarzschild black hole, and they're known to lower orders for more complicated situations involving spin or eccentricity. Okay, and an example as an example, I showed that that long expression for the phase evolution as a function of frequency, right? So you can compute that type of equation as well in this approach, and you get these very gigantic. This is just one coefficient. This is just the 6pn coefficient in that expansion of the phase. And they become enormously larger as you go to higher and higher PN orders. They don't even print in the papers the 22 PN things because it would take like the whole journal.
So, then can one obtain the 22 PN term from them somehow?
Yeah, I assume if you email Fujita, he will send you the 22 PN term, I believe, yeah. Yeah. Okay, so that's sort of the standard black hole perturbation theory approach, which has been going on for a long time. But this and this is all done in this radiative approximation that I discussed, but there's an approximation built into this radiative approximation, and we might worry about what that is. Essentially, in this radiative approximation, we're really only considering the energy loss due to gravity. We're only considering the dissipative effects. Okay, that's fundamentally what goes into this radiative approximation, right? So we're only accounting for energy loss to infinity or down the black hole horizon, but there are other effects which can modify the orbit, which will depend on the mass of the small body, which are not necessarily dissipative effects. Okay, there are so-called conservative effects that also affect the orbital evolution, which are not directly related to say energy going to infinity. Okay, so in order to get around this problem, you can't use this radiative approximation. You have to do something better, and essentially what you have to do is you have to solve the geodesic equation, but now supplemented by this, what we call the self-force, some force which is, whose acceleration is proportional to the mass of my small body, okay, which is the actual force that's perturbing my small test mass off of its geodesic orbit. Right? So if I want to do better and not make this radiative approximation, I actually have to evaluate this force in some consistent way. Okay? So an example of what some of these conservative type effects that the radiative approximation are neglecting are, well, just at Newtonian order, there's a very simple effect where if I just write, say, the relative acceleration of a small body going around a bigger body, right? So at lowest order, the acceleration only depends on the big black hole mass, say, right? But there's really an effect of the small black hole that, such that the actual acceleration, as we know from Newtonian theory, is really the sum of the two masses. Okay? So this is an example of a kind of conservative effect, right? So in Kepler's law, for example, for a binary, there's a correction that depends not only on the mass of the bigger object, but a mass on the smaller object. Okay? So that's one simple kind of conservative effect. Another kind of conservative effect would be a small shift in, say, the rate of periastron advance of Mercury around the Sun due to the mass of Mercury. Okay, that's another kind of conservative effect. And in general, all of the orbital frequencies, if I had some complicated curved geodesic, they're going to get shifted around a bit because of, with some dependence that's proportional to this mass of this small particle. Okay, so I can essentially think of the effective potential and say the Schwarzschild spacetime is getting adjusted a little bit when I include this mass of this small body. There are also shifts in the location of the innermost stable circular orbit. So usually this quantity we say occurs at a value of 6m for Schwarzschild. Okay, but when I actually worry about the mass of this small particle, say again? Okay. Okay, so why don't I will skip through some of this quickly. Okay, so when we talk about this self-force effect, so we can write this self-force into basically different kinds of pieces. We can write it in terms of, first of all, we can write it in an expansion in the mass ratio. So there's a first-order piece of this self-force, okay, that's proportional to, say, the mass of my compact object, okay, or my smaller black hole. And there's corrections that go like the square, et cetera, okay? But at each of those orders, there's dissipative pieces and there's conservative pieces. So there's a conservative piece of that force, which is what enters this radiative approximation, which is just what produces the waves that go to infinity and down the black hole horizon. But there are also this piece of this self-force which sources these conservative effects, okay? Like this change in the periastron advance rate, for example. And these two types of effects, they affect the phase evolution in different ways. Okay, so this dissipative effect, okay, this affects the leading order piece of the phase evolution if I were to do an expansion in the mass ratio. Okay, so this is the reason why this radiative approximation actually is pretty good, okay, because that's the main effect. That's the big effect, is just due to this dissipative piece of the self-force. However, if you look at where does this conservative piece come in, this conservative piece comes in at another order in the mass ratio. But if you look at how this term scales, you basically have an epsilon divided by an epsilon. So essentially you get a potentially order unity correction to the phasing. And as we talked about earlier, you have to worry about order unity corrections in the phasing if you want to do match filtering, to measure your parameters very accurately. So even though this conservative effect is very much smaller by a factor of the mass ratio from this dissipative effect, we still need to take it into account. Okay? And in addition to this conservative effect, there's recently been discovered this new phenomenon called transient resonances, which actually cause an even larger correction to the phasing, okay, that comes in, at a power basically of 1 over the square root of the mass ratio, okay, which is basically due to a phenomena where when the orbit passes through a point where certain frequencies are in a rational integer ratio, okay, I essentially can get an amplification. This dissipative self-force effect essentially gets amplified and causes this weird phase shift, which basically acts like a sudden glitch in my phase evolution, okay, and it's very much larger than this conservative self-force effect. So this is really only discovered very recently. This effect and
have been calculated for generic orbits also, or is only
which effect?
These self-force leading and higher circles.
Have they been calculated for generic orbits? No. I'm going to discuss exactly what's been calculated in a moment. Okay. So the basic procedure now to do this self-force evolution is, we wrote down this equation before. You have this geodesic equation supplemented by this self-force. What the self-force is it's a gradient of essentially the metric perturbation, okay? But it's not the entire metric perturbation, because actually the metric perturbation has a piece which diverges at the location of the particle, okay? If I imagine this point particle, it has a Coulomb-type divergence. Okay, so when you actually compute this self-force, you need to subtract out this singular divergence. Okay, so that's ultimately this procedure that you have to do. You have to compute essentially the retarded metric perturbation, so the full metric perturbation that you get by solving the wave equation. Okay, given some orbit, I construct my stress-energy tensor along that orbit. I compute the retarded metric perturbation. Okay, and then I subtract out the singular piece of that metric perturbation, and then I take a gradient of that regularized metric perturbation. That gives me the self-force, and then that tells me how to perturb away from my geodesic orbit. Okay, and then I can iterate this procedure, and that gives me a way of evolving these Emery orbits that's more accurate than this radiative approximation. Okay, so what's been done along these lines? So really Lior Barak's group is sort of the leaders in this area, and so far what they've done is they've implemented this numerical they've implemented a numerical scheme to solve all those equations I listed here for Schwarzschild only, okay, for eccentric orbits. So you can do eccentric orbits in Schwarzschild. Other groups have also implemented their own codes. I think they've only done circular orbits, and there have been cross-checks between the different groups, and everybody agrees very nicely. One of the interesting things that Barak and Sago computed is they computed this shift in the ISCO, which I talked about. So instead of, say, the ISCO frequency being at, the 6 to the minus 3/2 power, this is related to the 6m that you're familiar with, you get some correction which depends on the mass ratio. Okay, and this was a very important result in this field, because this is essentially a gauge invariant quantity that you can use to compare various different approaches to. Okay, so this was sort of the first sort of important number, I would say, that was computed from this self-force calculations. And there were a variety of comparison studies that people did, comparing all the various post-Newtonian and effective one-body approaches and numerical relativity comparisons to this ISCO shift. And you can find that post-Newtonian methods actually can do surprisingly well for certain approaches. Another interesting thing that was computed is the correction to the periastron advance rate. So this conservative correction I talked about to say, what's Mercury's periastron advance rate? How does that depend on the mass of Mercury? So I'm going to talk about that in more detail in a moment. People have also computed what are the corrections to the orbital energy and orbital angular momentum due to from the Schwarzschild values, which are known from MTW, say. They've computed the corrections due to the self-force, okay, due to this dependence on this small mass from those textbook expressions. Okay, and there have been various comparisons done with between post-Newtonian, numerical relativity, and effective one-body approaches. And recently there's also been a better estimate done of how does this full self-force evolution compare with this radiative approximation. In other words, how bad is the radiative approximation if you actually evolve an orbit using the radiative approximation and not using it, okay? And you find, as you expect, an order unity phase offset, over the course of an inspire. Okay, so one of these. So how long do you want me to? When do you want me to stop? I know. I've got about like 15% left.
So, I'm happy with you.
Yeah, finish.
Okay, you sure? If anybody wants to leave, I won't be insulted. No problem. Okay? Okay, so...
it's probably going to be more technical. If people want to leave, that's fine.
Yeah, it's going to become more technical now, so it's fine to leave. I leave all the time in talks I don't like, so it's okay. Okay, so one of the interesting results which was computed is this correction to this periastron advance rate. So recall, this is the formula from just... that Einstein computed, essentially, which gives you this 43 arc seconds every century for Mercury's periastron shift. Okay, and so we can express this periastron advance rate, so the change in angle per orbit, okay, in terms of this quantity k, which is just the ratio of the radial orbit frequency and the azimuthal orbital frequency. So I'm just going to define this quantity k for something I'm going to show in a minute, and this is some work done by a comparison study between the SXX Harold's numerical relativity group. Yep, pay attention. And the self-force work by Lior Barak and Sago. And so essentially what this is a comparison of this quantity K, okay, which is a measure of this periastron advance rate using various different methods. Okay? So in blue, you're essentially seeing the numerical relativity result. Okay, and this is for a equal mass ratio and for a mass ratio of 1 to 8. Okay, and on the bottom half, you're seeing the deviation from the numerical relativity result for different types of calculations. So you see Schwarzschild, the regular Schwarzschild result doesn't do so well. The effective one-body approach, which we'll talk about later, does pretty well. If you use this GSF as the gravitational self-force approach, this actually does very badly, okay, but it does better, of course, when you have a smaller mass ratio, okay, as you expect. It does much better. But what's especially surprising, and PN does, you know, about as well as you expect it to do in this sort of situation. But what was very surprising from these results was that if you make a specific, if you make a specific change in how you identify the mass ratio, you actually get a dramatic increase in improvement. So for example, I can write this quantity K for the self-force results in terms of the Schwarzschild value, times some correction which depends on the self-force that I have to compute. Okay? And this correction is linearly in the mass. It's linear in the mass ratio. Okay? Now if I just replace the mass ratio with this other quantity, the reduced mass ratio, which is what appears in all the post-Newtonian expressions. Okay, this is sort of the natural quantity that shows up. If I just make this simple identification, so the expression is the same, all I've done is I just changed this Q to an eta. Okay, then I get this solid blue line here, which you can see agrees very, very well with the numerical relativity result. So just making this very simple change of variable gives you a dramatic improvement in, in your results. Okay, and this is essentially something which is sort of really behind this effective one-body approach, and even in Newtonian theory, you have this property that you can describe the orbit of two binaries by changing your variables such that I instead of modeling two objects going around their center of mass, I have a reduced mass particle going around an object which has the total mass, right? So this feature of Newtonian theory is very much a robust feature we see in relativistic simulations. And that's really what's going on here.
A simple way of seeing why symmetric mass ratio would be a better parameter than the normal mass ratio?
Of seeing why, aside from the sort of fuzzy argument I just gave you, not that I can think of off the top of my head. I mean, we see this in many situations. I'm not aside from sort of the analogy with Newtonian theory, I'm not sure if there's a deeper explanation.
If you would compute the delta phi for Mercury with that mass ratio, whatever that is, a million or something, yeah, how much would be that? What do you think?
It would be proportional. It would be proportional to the mass of Mercury divided by the mass of the Sun. So whatever, that's like a really small number. I don't know what it is exactly, but it's some tiny, tiny correction. I don't think we can see it.
What about for binary pulsar? That we can compute.
For a binary pulsars, the objects are of comparable mass. So effectively, we use that. We effectively in the post-Newtonian calculations, they are already including this effect. Okay, this so-called conservative correction is already encapsulated in the calculations that measure this periastron advance rate.
But it's actually very well known that the K1P actually almost the same as the test particle one.
So you're saying there's no eta correction at 1 PN? Is that what you're saying?
Yeah, that has been pointed out by Cliff many years ago.
Okay, well then if we could measure by observing pulsars longer the 2 PN effect, there would be an effect. I'm sure, I know for sure that there's an eta correction in the 2 PN effect.
Yes, there is an
So I'm not sure if we're sensitive to that yet, but in principle with long observations of a binary pulsar, you would be sensitive to that accumulated phase difference. Okay, so that's all for black hole perturbation theory. Then there's this effective one-body approach. Okay, so this effective one-body approach is basically a synthesis of all sorts of different techniques. Okay, and the basic idea behind it is to provide some sort of quick semi-analytic way to generate a waveform that includes the entire shebang: the in-spiral, the merger, the ring band. Okay, it's in one self-contained formalism. And it contains input from basically 3 different areas. There's a post-Newtonian piece of the input, which is basically a way of extending the post-Newtonian dynamics so that it goes past the adiabatic regime, okay? This regime in which you assume the orbit decays very slowly and lets you go past this regime into this regime where, say, the radius of the orbit is decaying much more quickly, okay? There's a piece from black hole perturbation theory where you're encapsulating this ring down piece of the waveform. And there's also input from numerical relativity because you introduce these various extra parameters which you then try to fit against various numerical simulations. Okay? So again, the basic approach for this post-Newtonian piece, sort of the key ingredient of this EOB is really effectively a remapping between the two-body dynamics in the standard post-Newtonian approach. Okay, you take that Hamiltonian, there's a way to essentially construct an effective Hamiltonian, which is basically equivalent to the Hamiltonian of a test particle, or rather a particle with a reduced mass moving around a black hole whose mass is the total mass. So it's a sort of trying to implement this idea I just talked about that you have a Newtonian gravity, but sort of in a relativistic sense. And what you effectively get out of this mapping is a metric which looks like the Schwarzschild metric, but is deformed in terms of a parameter eta, which is just the mass ratio. Okay? So I essentially have some deformed Schwarzschild metric, and I can then construct the new dynamics of my reduced mass particle on this effective Schwarzschild geometry. Okay? And so from this geometry, I construct a new Hamiltonian, okay? And I can introduce now, in this metric is now where I can start to introduce new fitting features, right? So I get some sort of exact analytic solution that depends on to what order I know the standard post-Newtonian Hamiltonian, and then I can introduce some new free parameters into this metric, which I can then try to fit to the numerical relativity simulations. So once I have this metric, I construct this Hamiltonian. I can then write down Hamilton's equations and solve them for what's the conservative pieces of the orbital motion. Okay? I have to supplement this, of course, with some dissipative piece of the motion. Okay? So the way you do that is you essentially add an extra term to Hamilton's equations, which is essentially related to the energy flux. Okay? But you express the energy flux in some complicated way that depends on the waveform which you're actually trying to compute. Okay? So there's sort of this iterative procedure that goes on. Okay? And this procedure is actually more complicated than I described, especially when you get the spinning cases. So this is just to give you an overview of how it works. So once you construct essentially the dynamics of the orbit, then you want to construct the waveform. And this is also sort of a little bit complicated. You essentially write the waveform in different pieces. First you have this in-spiral and plunge piece, okay, the part that takes me to everything except the ring down. Okay, and I rewrite this waveform in terms of a Newtonian piece, which just looks like the regular Newtonian order waveform that you can easily compute. That's a function of the momenta and the coordinates. And I supplement that with various kinds of corrections that account for the fact that the orbit is in this non-adiabatic regime where I'm starting to get very large radial variations. And also this extra term encodes all these various post-Newtonian corrections in a way that attempts to improve their convergence properties. Okay, so there's this sort of very complicated way of writing down this waveform, which I'm just sort of illustrating schematically here. And so this is sort of this gives me the waveform up to essentially the ring down part, and then I need to write down another piece of the waveform, which basically is just an exponentially decaying sinusoid. Okay, and I know what these quantities are, these frequencies and these dampening times. These just are known from black hole perturbation theory. If I just have a single black hole and I perturb it, I can measure these quantities. What I don't know is what these amplitude coefficients are. Okay, but these are determined essentially by matching this waveform to this waveform at some particular region near the merger. So in some matching region near the merger, I take this in-spiral plunge waveform and I take this ring-down waveform and I match them, and that gives me these coefficients. So now I have the entire waveform as a function, in terms of solving this complicated ODE. And so people have done various comparisons with numerical relativity in this case as well. And I mean, the general punchline is you can basically get very, very good agreement with the numerical relativity simulations through all phases, in-spiral, merger, the whole thing. You get very good agreement. Of course, it depends on what sort of ingredients you put into the EOB versus what your numerical simulation has. So, for example, right now, treating the case of very, very high spins is still, the EOB is still not quite up to the task, but if they tweak it a little bit, eventually it will be, presumably, right? So you're always modifying this EOB formalism and putting in new ingredients and trying to sort of tweak things here and there and introduce new parameters to fit to the numerical simulations. And by putting in enough ingredients, you effectively build up a sort of a fitting formalism that lets you match the numerical simulations very well, but are much less computationally costly. So you have a question?
So you introduced, I mean, you were effective Hamiltonian that you were constructing for the one-body problem, then you were introduced to parameter in your metric, right?
That's one of the parameters, but there are many other, that's one place where you can introduce a parameter, but there are many other places. For example, in this, this quantity here, this sort of rest of the waveform, which I'm not writing down, there are actually many other places to like add extra parameters, right? So you can introduce several other parameters here.
You were doing the matching part.
That's right. So there's some number, I forget what the number of parameters is in the latest model. It's on the order of 5 or so parameters that you introduce, and then you just tweak them and compare it to numerical simulations until you get a good match. Yes?
So you will have only like one function which would go throughout the parameter, or you will have like a different, so you have one which will only go for non-spinning, and then you have some other function.
I'm not, you have a function that depends on free parameters. What do you mean by? Oh, you mean if you change to a spinning from non-spinning? I mean, in principle, it's possible that you could like come up with a new model once you do this. I don't remember the details of what new, of all the different ingredients they introduced, but as you go to a more complicated model, you might decide, okay, I now want to change my function, my functional form and its dependence on these free parameters, and do it in a different way that presumably encapsulates all the simpler cases as well, right? So it's not like you suddenly have to change your, if you can do the spinning case, presumably you've constructed it in such a way that it can do the non-spinning case as well, right?
It has been done with this first state case only. You guys have done the card and other cases.
So yeah, so this has been done, this sort of mapping has also been worked out sort of in the Kerr case. So for an effective spinning particle around a Kerr black hole, that has also been worked out. It's simpler to talk about the Schwarzschild case, so I just talked about that. But that's given in some of the other papers I wrote down there. Okay, and so lastly, there's this other approach which Ajit is really the expert in, which is called this IMR, or phenomenological in-spiral merger ring-down approach. And essentially what you're doing here is you're trying to come up with a simple analytic waveform in the frequency domain, which you can use to basically search through the LIGO data in a very computationally efficient way. So you start out basically by taking some numerical simulation and taking a post-Newtonian waveform and constructing a hybrid waveform, which is essentially a matching between these two waveforms that can extend through both the post-Newtonian and the numerical relativity regime. And then you write down some sort of functional form that looks like that function I talked about much earlier, where I write the Fourier transform of my gravitational wave signal in terms of an amplitude piece and a phase piece. Okay, and then I split each of these pieces, the amplitude and the phase piece, into a piece that comes from the in-spiral, some correction due to the merger piece, and a piece that comes from the ring down, and I essentially match these two pieces together, you know, and the coefficients are constrained by enforcing continuity and smoothness, and you also try to adjust various free parameters that you introduce to the numerical simulation, such that you get a good fit over a range of numerical simulations. Okay. So, I'm sorry, Ajit, I won't talk about this anymore. So, so the future, what is left to do? So I think sort of the motivation for why we want to do better really comes from this issue of systematic parameter errors. So you know just from like your introductory lab classes that you know, you have two kinds of errors in physics. You have statistical errors, which is really telling you how precisely you can measure some quantity, right? So that's sort of like LIGO constrains us to be able to measure parameters of a binary to within some degree. That just depends on the noise level of the LIGO detector and the signal strength of your particular source. So that's one kind of error. And that's kind of like, what's the spread in my darts around the target here, okay? But then there's another kind of error, which is the systematic error, which is essentially due to your lack of understanding of your experiment or of your model that you're using, okay? And that's the type of error you make when you throw all the darts in the same place, but you miss the target all the time, okay? And of course the problem is that in the real world you don't actually know where the target really is, so it's very important that you get some sort of handle on what the systematic error is, okay? This is some work that I looked into recently, trying to estimate what these systematic errors are. I'm just going to skip it because it's going to take too long for me to explain, but sort of the punchline is that you could try to estimate what sort of errors are you making by ignoring higher order pieces of the waveform that you don't know. And if you want to know your masses, say, to within some threshold, like say 10%, then you would actually need to go to higher post-Newtonian order in, say, your non-spinning waveforms. Okay, and likewise, for this tidal love number that I talked about earlier, if you ignore, say, these higher order pieces of the waveform that you don't know, but which are actually at the same or lower orders than your tidal effect, okay, you actually end up introducing a very huge error in your tidal love number, a very large systematic error that's essentially so large that the parameter is unmeasurable if you're just using a post-Newtonian approach. Okay, so what is left to be done in sort of these various analytic schemes? I think going to 4pn order in the post-Newtonian waveforms would actually be very useful for just getting very accurate mass determinations with LIGO for, say, binary neutron stars. And there's been some partial work on computing 4pn, but really only the conservative pieces. It would be good to know even to 5pn to get a better handle on the tidal effects as well. Spin effects are also only known to 3.5pn order, and since they start coming in at 1.5pn order, it's actually 1pn order less than we know the one relative pn order less than we know the point particle effects. So it'd be good to know these spin effects to higher order as well. Okay. So that's just in the post-Newtonian case. So what about in this extreme mass ratio in spiral perturbation theory? So in this area, I think there's very much more work that can be done. In the Schwarzschild case, I think the self-force computations are basically understood. But there's still various issues. The Kerr case, I think, is still, people have been working on this, but it's still not fully implemented. I think there's still a lot of development in the Kerr case. These orbital evolutions that have been done are still actually not fully consistent orbital evolutions. So when I talked about this work by the Orberach's group, they actually are still making a simplifying assumption when they do their evolutions, in that they take a geodesic orbit and they evaluate the self-force around that orbit before updating to the next orbit. Okay, so you're effectively making this, you're accounting for the conservative effects, which you're not doing in this radiative approximation, but you're still making some type of adiabatic approximation when you do these evolutions. So, and in principle, you might, the size of these effects should be estimated, but it seems like many effects that you initially ignore end up being important, so it's likely these effects are actually going to need to be taken into account. This resonance effect also is actually very important and will need to be modeled, but it actually makes the modeling of these Emery systems very much more difficult because it introduces an additional dependence on another orbital parameter, which we thought we essentially didn't have to know about. So this transient resonance effect is going to dominate over this conservative self-force effect, which people have spent years trying to compute. Okay, so this is sort of another area that I think is going to have a lot of future work. Also, in all of this work, the spin of, say, the smaller black hole has been totally neglected, but actually the spin of that smaller black hole is on the same size. It produces a correction to the phasing, which is on the same size as these conservative self-force effects, which we've been trying so hard to compute. So that also needs to be folded into these calculations. Effectively, that adds a spin curvature coupling term to the right-hand side of the geodesic equation. And in case people run out of things to do, then you really would also like to go to a second order in perturbation theory, because probably that will also cause some dephasing, which for these in-spirals that have millions of cycles is not going to be totally negligible if I want to get very high precision. So there's always something left for theorists to do. Also, these analytic black hole perturbation theories, which have been computed to 22 post-Newtonian order. Okay, I think there's more work to be done in that area because that's only been done for the non-spinning circular case. You can imagine extending those calculations to more complicated geometries. For the effective one-body approach, this is pretty much well developed now, I would say, for aligned spins. The processing case is not quite fully developed, but I think it's approaching it. If it's, it's almost there, I would say. Yeah, right, okay. So probably in the next few days, we'll see some new developments on that. Also, incorporating neutron stars, into this effective one-body approach is also, work has been done on this, but I think that probably can be developed a little bit further. And likewise for neutron star black hole binaries, I don't think that's really been developed very well in this effective one-body approach. For the phenomenological waveforms that Ajit has worked a lot on, I think this aligned spin case is, basically we know how to compute these types of things in that case, but you can imagine ways of improving the models. Precession effects have not been included, and there's been some work on making these phenomenological waveforms for neutron star black hole binaries, but this is also very early in this period of work. Okay, so finally, the summary. So if you didn't remember anything, I hope you'll at least remember that starting around 2017, we hope we'll actually detect gravitational waves, a couple events per year. There's a whole bunch of various analytic approaches and numerical approaches we use for modeling these waveforms, and we need to use all these approaches because ultimately we want to extract science from these, hopefully, eventually, detections that we see. And numerical relativity isn't enough. We need to use all these various analytic methods to treat all these different cases that I talked about if we want to model the waveform to very high accuracy. I didn't talk about it too much, but there have been many, many cross-checks done and comparisons between these different analytic and numerical methods, and there's been generally excellent agreement in most cases. So it's been sort of surprising how well many of these analytic methods do when you compare them to fully numerical approaches. So as I just talked about, I think we probably need higher post-Newtonian waveforms if we want to control these systematic effects, including the spin effects as well as point mass effects. And in the small mass ratio case, I think that's the area where there's sort of the most work that's left to be done. But fortunately, LISA is over a decade or two in the future, so we have plenty of time to work that out. So thank you for indulging me in some extra minutes. Yeah.
Okay.
Which approach do you think will be best for an neutron star rotating around supermassive black hole?
So for that, a neutron star around its effect is essentially what you would use. So the fact that it's a neutron star isn't going to change anything very much. Okay. Because the big black hole is so big, the tidal effect is actually quite small. So the neutron star will actually get swallowed up before it gets tidally disrupted. So you can effectively consider that neutron star to be a point particle, just like you would, say, a 10 solar mass black hole.
But in case it is a stellar mass black hole and a neutron star, how much you expect this ISCO radius to change?
Okay, so if we have a stellar mass black hole and a neutron star, that's like a so in that situation, the ISCO itself is not a very well-defined quantity anymore. So this notion of an ISCO really relies on sort of this separation of mass scales. Okay, so the ISCO sort of goes away. Your orbits look like, if you saw this little, this little inspiraling figure here, it's hard to say where the ISCO is here because there's not just a sudden obvious transition point where you go from an adiabatic inspiral to a plunge. That transition point is blurred. So, I mean, you can compute something that's an ISCO, but it's not a well-defined quantity in the comparable mass case.
But I mean, the effective radius for any sharp transition can be seen is very difficult.
In the comparable mass case, yes, I think that's difficult to say.
Order of 10, mass ratio order of 10.
Okay, so now if you're talking about, if you have a neutron star going into a black hole that's around 1 to 10, then if you look at these numerical simulations, so Shibata gave a talk where he showed this, then you can see sort of more of an abrupt transition in the waveform in this type of case. So I don't know if you want to call it an ISCO or not, but there is certainly a feature there.
Any questions? Okay, anyway, Marc will be here for the next 2 days, so anybody has some questions, catch him up.
Yep.
Thank you very much.